Hi, we're Josephine, Herbert, and Sarah, and we will be presenting on Group 16 on the periodic table, the chalcogens. First, we'll go over the property trends. Going down the group, metallic properties increase. Tellurium is classified as a metalloid, and polonium and livermorium are classified as metals. The melting point, boiling point, density, atomic radius, and ionic radius all increase going down the group, and electronegativity, ionization energy, and electron affinity all decrease going down the group. The most common oxidation state for all the elements is -2. Oxygen can exist in +2. Livermorium is predicted to exist in +2 and +4. Sulfur can exist in +4 and +6, and selenium, tellurium, and polonium can exist in +2, +4, and +6.
The chalcogens, as according to the octet rule, are able to accept 2 electrons along with their 2 existing lone pairs. With 2 single bonds, the bent angle produced is between 90 and 120 degrees. However, chalcogens are also able to create a third bond and become a cation, forming a trigonal pyramidal structure with 1 lone pair. Due to their bonding nature, chalcogens commonly form double bonds. We can also look at the reactivity of each of the individual elements within the group 16. Oxygen and sulfur are 2 of the commonly found and used elements within the chalcogens. Oxygen is the second most electronegative element, right after fluorine. It forms compounds with almost all of the chemical elements, including some of the noble gases under certain conditions. Additionally, oxygen commonly bonds with many metals and metalloids to form oxides. Going down the group, we then reach sulfur. While sulfur-sulfur double bonds are far weaker than oxygen-oxygen double bonds, sulfur-sulfur single bonds are much stronger than oxygen-oxygen ones. Thus, sulfur also has the most known allotropes, as it is able to readily form long chains and rings of sulfur atoms through covalent bonding. At higher temperatures, sulfur also exhibits a higher viscosity. Sulfuric acid is a commonly known compound which contains sulfur. Selenium is a moderatively reactive element, allowing it to be a semiconductor and a catalyst for many different reactions. Tellurium, on the other hand, is a relatively unreactive element that does not even react with oxygen. Polonium is a radioactive element with 2 metallic allotropes. Like other radioactive elements, polonium exhibits traits such as its own half-life. Finally, livermorium is a chemically synthesized superheavy element with a rapid decay.
Chalcogens can interact with other groups on the periodic table. When they form compounds with metals, they are referred to as chalcogenides. We see superior electronic, optical, and semiconducting properties in these compounds. Cadmium sulfide is one such chalcogenide that has been used over generations. It is commonly used as a pigment, more well known as cadmium yellow. However, it also has applications in optoelectronics, where it has been used as a photoresistor in items like nightlights. Chalcogens can also interact with pnictogens. Their resulting compounds are used in items such as strike-anywhere matches, insecticides, and even in quantum dots. Nitrogen oxides are one such interaction between the 2 groups, which are used in items such as rocket fuel. The space shuttles made use of these nitrogen oxides in their rocket fuels. When chalcogens interact with halogens, they form chalcohalides or chalcogen halides. One such chalcohalide is dioxygen difluoride. This compound was used at the Los Alamos National Laboratory to synthesize plutonium hexafluoride, which is used in nuclear weaponry at low temperatures, solving an issue of decomposition of the plutonium hexafluoride at the previously very high temperatures necessary for synthesis. There are many important reactions involving the group 16 elements, and this includes the combustion and oxidation reactions with oxygen. One such reaction is the combustion of glucose, the reaction shown here. This is a vital part of cellular respiration, the process in which inhaled oxygen combines with foodstuffs to release energy to be used in bodily processes. This reaction is essential to life. Another important reaction is the formation of sulfuric acid from fuming sulfuric acid or oleum. This is one of the most important industrial reactions in the contact process, the modern industrial method of producing sulfuric acid. Sulfuric acid is used in a variety of applications, from fertilizers to the purification of petroleum, making it a very important reaction.
Chalcogens are found and used within many aspects in the world around us. For example, oxygen is what makes up the ozone layer within the Earth's atmosphere, which protects us from the sun by absorbing ultraviolet radiation. Additionally, we ourselves use oxygen for respiration, just like almost every other living organism. Hemoglobin carries oxygen to cells across our body so that it may act as the last electron acceptor in the electron transport chain, which creates most of the ATP that we use as energy. Sulfur, when mixed with potassium nitrate and powdered charcoal, creates gunpowder. Selenium, due to its chemical properties, allows it to be commonly used in photoconductors in devices related to xerography, photoelectric cells, and other semiconductor devices. Additionally, when it is mixed with another chalcogen, sulfur, selenium creates a brilliant red color for glass. Tellurium is also used for tinting glass, creating a yellow-green hue. Although not very reactive, tellurium also has uses as a catalyst. Specifically, tellurium is a vulcanizing agent and accelerator to improve heat resistance in the rubber industry. Polonium, due to its exothermic radioactive decay, is used as a power source in many applications, such as satellites. Finally, livermorium, as noted before, is synthetically created. It is currently just used for research of super heavy elements, as it is highly unstable.
An interesting fact about the chalcogens is their role in cancer theranostics. The green synthesis of nanoformulations involving sulfur, selenium, and tellurium are promising tools for cancer research. The synthesis of chalcogens and chalcogenides using plant extracts and their purified biomolecules have been recently studied to determine their ability to prevent, diagnose, and treat cancer. A property of chalcogens at the nanoscale level that causes them to be of interest is biocompatibility. Additionally, sulfur is non-toxic and biodegradable, and selenium is optical and photoconductive. Selenium nanoparticles have demonstrated antioxidant, antimicrobial, anti-cancer, and photocatalytic activities. They were shown to prevent the release of free radicals that cause DNA oxidative damage. They bind to metal ions such as copper and intracellular proteins that are abundant in cancer cells, causing apoptosis of the cancer cells. Apoptosis is programmed cellular death, also coined as cellular suicide. Tellurium nanoparticles have demonstrated antioxidant, antimicrobial, and anti-cancer activities. Like the selenium nanoparticles, they also serve as free radical scavengers, and they also bind to cellular protein in DNA, causing cell death via mitochondrial-dependent pathways. Sulfur nanoparticles have demonstrated anti-cancer ability in oral cells. Like selenium nanoparticles, they bind to metal ions such as copper and intracellular proteins that are abundant in cancer cells, causing the cancer cells to go through apoptosis. They also interact with intracellular and membrane proteins, which alters membrane permeability. This can also lead to cellular death.